Okay, I think we're at the point where we might want to start reviewing some of the rules of exponents. We should be fairly comfortable with a lot of these rules. We may need to factor or expand them out from time to time, but I think a lot of us are starting to pick up on these rules. So let's take a look at them. So the first rule is simply when we're multiplying powers with the same base, we add the exponents. In other words, let's say I have an example where I have 5 to the power 3 times 5 to the power of 7. I'm simply going to just add the powers. Add the exponents. So I'm going to have 5 to the power of 3 plus 7, which is 5 to the power of 10. And I know that because essentially if I factor this out, I'm going to factor out 3 fives and 7 fives. The next rule is that when we have a power to a power, we simply can multiply the powers. Again, just kind of using the same values as before. If I have 5 to the power of 3, and that's to the power of 7, that's going to be the same thing as saying 5 to the power of 3 times 7, which is the same as 5 to the power of 21. The reason I know that is because if I expand this out, 5 to the power of 3, I have 3 5s being multiplied. And if I do that 7 times, since it's to the power of 7, I'm going to essentially be multiplying 5 21 times altogether. Okay, some of the ones we might be having a little bit more difficulty simplifying as of right now is when we are dividing powers. We can simply subtract the powers because of the giant 1. So this one I'll actually factor out to show us, but let's say I have, 5 to the power of 8 over 5 to the power of 3. I'm just going to factor it out. 5, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. And with the giant 1, I'm going to simplify 3 5s from the numerator, 3 5s from the denominator. So what I have left is 1, 2, 3, 4, 5, or 5 to the power of 5. And essentially the shortcut is 5 to the power of 8, and I just subtracted 3 powers of 5, and that gets me 5 to the power of 5. This one isn't a shortcut or anything. This is more just understanding a power with an exponent of 0. So if there's anything to the power of 0, it's going to be 1. In other words, if I have 5 to the power of 0, that doesn't equal 0. It's not 0. It doesn't equal 5. It actually equals 1. And we're going to actually bring back the previous property, the one where we talked about subtracting the exponents, to make sense of that. If I have 5 to the power of 3 over 5 to the power of 3, to simplify that, I'm going to do 5 to the power of 3 minus 3, which is 5 to the power of 0, which equals 1. Another way we could look at that is 5 to the power of 3 is simply 5 times 5 times 5. And same thing with the denominator, 5 times 5 times 5. I use the giant 1 to simplify, and that's going to equal 1. So when there's a non-zero value put to the power of 0, it's going to equal 1. Finally, for the last property, and this is this is also something that's confusing us a little bit, and I should have added something to that. But when we have a negative exponent, it's the same as the reciprocal of the positive exponent. It doesn't make the value a negative. Okay. So what I mean by that is if we have 5 to the power of negative 3, what that means is that we're going to have 1 over 5 to the power of positive 3. If I have, let me do this in a different color, 1 over, let's say, 4 to the power of negative 5, that's going to equal 4 to the power of 5 over 1, or just simply 4 to the power of 5. So the negative exponent makes me rewrite it as the reciprocal of the positive exponent. Okay, and we learned this because we kind of noticed the pattern 5 to the power 3 is just really 5 times 5 times 5. And then 5 to the power 2, we're just dividing by 5. So that's going to be 5 times 5. 5 to the power 1 is just 5. Because we're dividing by 5. Divide by 5 again. 5 to the power 0 is 1. Divide by 5 again is going to be 1/5. Divide by 5 again is going to be 1 over 5 to the power 2, and so forth. Okay, so hopefully this quick review helps us out.